Okay, in this video we will see how to write the small signal model of few active load amplifiers and try to find out what is its voltage gain and output resistance. So first we shall consider this circuit. So in this circuit, this is output is taken here and input is applied here. The terminal that is common is source, so this is a CS amplifier. This is a CS amplifier, and now let us, since we are supposed to write the AC small signal model, so let us write the first thumb rule. Let us replace this by AC ground, that is VDD by AC ground. So this is M2, and this is the Vout point. Here I'm applying the input voltage. This is M1. Now fine. Now since it is AC grounded, this is over here. So this is my load resistor. This is having effective resistance of 1 over GM2 in parallel with R02. It's now AC grounded. Here I can write it. This is my Vin. This is M1. This is the V0 point. This you can effectively write it as equal to 1 over GM2, because 1 over GM2 in parallel with R02 is very close to 1 over GM2, because its resistance is very small compared to R02. So now I can replace it by something like this. Now this is Vin grounded, AC grounded, so this is my V0. This is 1 over GM2. This is M1. Now let me replace this M1 by its AC equivalent model, which is nothing but GM1 VGS1. Since we are assuming lambda to be non-zero for both of them, so this will have an internal resistance of R01, and this resistance is 1 over GM2. This is the V0 point. This is gate, drain, source, input voltage. This is VGS. So now, of course, I can write V0 as equal to minus GM1 VGS1 multiplied by R01 parallel with 1 over GM2. Since VGS1 is equal to Vin, I can write V0 by Vin is equal to minus GM1 into R01 parallel with 1 over GM2. This you can approximately write it as equal to 1 over GM2. So this gain becomes minus GM1 by GM2 in approximate gain. This is the gain of the amplifier. To find R out, we know that how to do it. So of course, as we see in the previous video, we make the input 0. This is Vin equals 0. At the output terminal, you apply dummy source Vx and find out what is the X. So this is my amplifier. So to this amplifier, let me do the same thing here. This is my AC grounded M2. This is source, and I'll ground this also. This is also AC grounded. This is AC grounded. I'll apply a Vx source. So this is Ix. This is now M1. Since you know that you are looking towards the drain, it is R01. You are also looking towards the drain, but it is gate and drain are shorted. So this is effectively 1 over GM2. So R out is nothing but Vx by Ix, which is nothing but resistance looking up is 1 over Gm2. This is approximate value. In parallel with what is the resistance looking down, it is R01. So for this circuit, the gain is minus Gm1 R01 parallel with, of course, R01 in parallel with 1 over Gm2, which approximately comes out to be minus Gm1 by Gm2. The R out happens to be 1 over Gm2 parallel with R01. So if you approximately want to write it, this is almost equal to 1 over Gm2. This is R out. Okay, let us try to do it for this. This is your input terminal, this is output. Since input applied and output measured are with respect to this terminal, which is the source of this main transistor, this is also a CS amplifier. Let me repeat. You are applying the input voltage, measuring the output voltage with respect to a common terminal, which is in this case source. So that's why it is CS amplifier. To write its small signal model, let us replace this by AC ground. When you replace this by AC ground, and this is also AC ground because this is also DC voltage. Now this is how M2 is now looking. This is Vin, and this is my diode connected MOSFET M3, and this is now M3, this is M2. So now this is, okay, let me write this as M1. So what are the resistance looking up here? Since you are looking towards drain, it is R02. Now here you are looking towards drain and gate shorted, so this becomes 1 over Gm3. So actually what you have is now is R02 is now this is AC grounded, and this is your MOSFET Vin, which is now M1. The resistance looking down here is approximately 1 over Gm3. You can see this is also ground, this is also ground. Actually these two will come in parallel. So now what will happen now is they actually come in parallel and it will look like this. This is again Vin, this is my M1, this is AC ground. What is this? R02 and parallel combination of 1 over Gm3. So this is where you measure the output V0. So if you write the AC small signal model, overall thing, this is Gm1 into VGS1, this is plus minus VGS1, this is gate, source, this is Vin, this is drain point, and this is R01 corresponding to M1, and the resistance of M2, M3 will now look like R02 in parallel with 1 over Gm3, 1 over Gm3. This is AC grounded. So from this, okay, here where you measure the output voltage, so can I write V0 as equal to minus Gm1 into R01 parallel with R02 parallel with 1 over Gm3 into Vin. Therefore V0 is, what is V0? V0 becomes, sorry, V0 by Vin. If you write the gain, it's nothing but minus Gm1 into R01 parallel with R02 parallel with 1 over Gm3. If you want to approximate this, okay, approximation of these two is 1 over Gm3. Again, approximation of these two is 1 over Gm3. Ultimately you will have an approximate gain. Let me actually put it in a different color pen. So this is approximately equal to minus Gm1 by Gm3. This is AV, approximate AV. Exact AV expression is this one. Again, to find R out, of course R out finding is very easy. Of course, let me just redo it here itself. Let me ground this. Let me apply a source Vx here. Let's find out Ix. What are the resistance looking up here? It is R02. Of course, this will also come in parallel with this. So is it not parallel with 1 over GM3? And what are the resistance looking down here? It is R01. R01. Okay, that is in parallel. So resistance looking up is this much here, which is R02 in parallel with the resistance looking up here is, of course, you can simply AC ground this one to find R out. You can just do it like this. This is Vx. Find out what is Ix. This V0 is not there. So what is the resistance looking up? It is R02 in parallel with 1 over GMK, which is due to these two parallel combination. What is the resistance looking down here from the drain side towards drain? It is R01. So overall resistance is R01 in parallel with R02 in parallel with 1 over GMK. So I can write R out as equal to, R out is equal to now R02 in parallel with 1 over GM3 whole thing in parallel with R01. This is approximately equal to 1 over GM3. 1 over GM3. This is a very low resistance, low output resistance amplifier. This is an approximate thing. Okay, fine. Let us spend some time in finding the frequency response of CS amplifier. Let us write the small signal model of this entire network, even considering the capacitors. So because for finding frequency response I need to consider the capacitors also. So let us consider these two parasitic capacitance CGSO, CGDO. This is CGSO, CGDO. Fine. So now let me write this. I will write R1, R2 parallel here, because now by this time all of you know okay, why I am writing these two in parallel, because when you AC ground these two grounds are common, and this is my gate, source, a drain. This is GM into VGS. Let us assume lambda as 0. If lambda is 0, R0 is infinite, as I am not writing any R0. So this is my RD. This is RD, this is drain, this is V0, AC ground, this is CC, this is R signal, this is R1, R2. Let me also plug in to two capacitors, that is parasitic capacitance, CGSO and CGDO. This is CGDO between drain and gate. This is CGSO between gate and source. So now we know that this floating capacitance can be replaced using two Miller capacitances, one at this side and other one at this side. So this is capacitance C1, capacitance C2, which is derived out of this CGDO using Miller's theorem. So let me rewrite the entire thing. So my small signal model for my frequency analysis looks like this. So this is C1, this is CGSO, this is ultimately source, here this is GM into VGS, this is actually VGS. I have a capacitor which is it is C2, and this is RD, this is V0, this is CC, R signal, R in, so on. So this is AC ground, source, this is actually gate. this is drain. So we know that R in is given by R1 parallel R2. C1 is CGDO into 1 plus AV, that is magnitude of gain. C2 is CGDO 1 plus 1 over the gain. This is due to, this we call it as Miller's capacitances. So this is due to Miller's theorem. Now after doing all these things, I can actually put these two in. Okay, these two are parallel. The effective capacitance is C in. So what is C in now? C in is actually C1 plus CGSO. What is C out? C out is the C2. C out is C2. So my overall small signal model will look like this now. This is C out, this is RD, this is V0, ground, GM1 into VGS, C in, R in, CC, R signal, V in, this is gate, drain, source. So because of which we will have a frequency response which is something like this. So this is the frequency, this is the gain goes like this, so it is keep increasing. So this is how the gain is increasing, and then it becomes constant, and then it again comes down, and then it again reduces. See here, now you come down 3 dB from here. This is minus 3 dB down from AV max. AV max, that is mid band gain. This mid band gain is nothing but GM into RD magnitude. Suppose what is the magnitude of this? It's actually GM into RD. So when we come 3 dB down, you have this point and this point. This corresponds to, of course, 3 dB when the gain is expressed in dBs. So you are coming down by 3 dB down from AV max. So this is one frequency F1, this is other frequency F2. So you can see there is one more change in slope here. This we call it as F3. So now these are the three cutoff frequencies of this frequency response of the CS amplifier. Now when you actually write this, make sure that when you write this, whenever there is a change in slope happens, come down from 3 dB from the maximum. So where it cuts this frequency response, that is F1 here, similarly F2 here, and for F3 there is nothing like again 3 dB or 6 dB or 6 dB down or 10 dB down. Wherever there is a change in slope happens, so that is F3. So of course we need to approximately mention this. Now what is the bandwidth? Now one thing to observe is, so let us try to find out what are the frequencies values. F1 is equal to 1 over 2 pi CC into Rin. Of course we have done the theory part of this in detail in the classes. So this is what is F1, first cutoff frequency. Second cutoff frequency is 1 over 2 pi. It can be R out into C out. It is these two capacitances. This capacitance, this resistance will constitute F2, and this is F3, which is 1 over 2 pi R signal, that is this R signal, and C in. So don't simply combine some resistor, some capacitor. For the first one, it is these two capacitances. So this RC, you can see blue color is this is my blue color. Next is this R out and C out. This is my other this one. So this is F2. This is F2. And what is the third one? The third one is actually this. So you have this R signal and Cin. R signal and Cin. So that's what is this R signal and Cin. So these are the, let me just mention that this is that. F3 is due to R signal and Cin. So don't simply say this. So you have to be careful while understanding. Now one more very important thing to understand is, depending on the value of R signal, suppose if R signal value is less, then F3 is always greater than F2. If R signal is less, if R signal is more, then F2 may be greater than F3. That is, if R signal is more, then this F3 comes down, so F2 may be far greater than F3. So depending on the value of R signal, we will have these two interchangeable. It's not always F2 is here, F3 is here. Maybe while doing in the class we would have written this as F3, this as F2. It doesn't matter. Make sure that whichever comes first, whosoever frequency is less, that will be the bandwidth deciding thing. So what is the bandwidth? Bandwidth is actually, of course, this value will be very small. So bandwidth is minimum of F2 or F3, whichever is the least of these two. So that will be the bandwidth of my amplifier. So what is the gain? Gain is this AV max. That's the midband gain. So that's the entire story of this. So let us try to find out one more very important thing is that you can see this CGSO, CGTO are given as 100 nanofarad per meter. So this is a per unit distance capacitance. This is not in farad, this is per unit distance capacitance. So what is the exact meaning of this CGSO, CGTO is? Let us spend some time with this. Okay, let me write it here. Assume that you have a MOSFET. This is the MOSFET structure. This is how it looks. We know that here we're going to have the, okay, let me also write, this is my, correct? This is how it looks. Okay, let me rewrite this. Okay, for the time being. Okay, this is the oxide, this is my gate structure, this is, you can see, this is the source slightly penetrated beneath the gate, this is the drain. Assume that this is P minus, so then this becomes N plus, this is N plus. In a 3D structure, this actually goes like this. So this actually goes like this, and you can see this overlap is just penetrating till back here. So usually we know that this is the length of the transistor, this is width of the transistor. The capacitor that we are talking about is this overlap capacitance. The capacitance we are talking is this overlap capacitance. Okay, that is not visible. Okay, let me make this. This is the overlap. Can you see this? Some region is overlapping. So usually this lateral diffusion, that is going the distance that is penetrating beneath the gate structure, is not in our hand. Okay, I am talking about this lateral diffusion is not in the hand of the user, but user can define what is the width of the transistor. So we know that capacitance is given by epsilon A by T in general. where A is the area, T is the separation of the two plates. So this is epsilon width into, let me write it as L, this is W dash, L dash and T. What is this L dash? L dash is actually this distance, that is this distance L dash, and this W dash is actually, okay, let me write it as W dash. So this is the width. So now, is this W dash is equal to width of the transistor? This W dash is same as W. So now what will happen is, you have capacitance which is nothing but epsilon into L dash by T into W dash. So whatever capacitance that you are given, CGSO, which is so many 100 nanofarad per meter. So this capacitance is always predefined. So this is that per unit distance capacitance, which is nothing but 100 nanofarad per meter. If I multiply this with width of the transistor, then I'll get CGSO in farads. So now in this problem we have been given what is CGSO CGDO in nanofarads. So in nanofarad per meter. To actually know what is CGSO CGDO in farads, I have to multiply these two parameters, that is 100 nanofarad by, this has to be multiplied by 450 micrometer. So what is CGSO CGD now? CGSO was 100 nanofarad per meter, width is equal to 450 micrometer. Therefore CGSO in farad is nothing but 100 nanofarad per meter multiplied by 450 micrometer. This meter will go, what is this 100 nano into 450 microfarad. So this is the value now. So what is this now? It is 100 exponential minus 9 into 450 exponential of, sorry, this is 9 minus 6. So now the capacitance is 45 picofarad is CGSO. So you cannot substitute it as 100 nanofarad as the value, but it's actually 45 picofarad. So same as CGDO is CGDO in farad. So let us use these two, this value of CGSO CGDO, find out different cutoff frequencies F1, F2, F3. So it is 45 picofarad. So let me take here CGSO is how much? So let me substitute here. So CGSO is equal to CGDO is equal to 45 picofarad. But what is C in? It's actually CGSO plus CGDO into 1 plus AV magnitude. First I need to find out what is AV. So let me just do that. What is C out? This is equal to CGDO into 1 plus 1 over magnitude of this. But what is AV? AV magnitude is GM into RD, where GM is the root of 2ID KP W by L. So I don't know what is the value of, okay, W by L is given as, so we know this, we know KP, we need to find ID. So ID is equal to half KP W by L VGS minus VTO whole square. VGS is looking at this, it is VDD, okay, it is VDD into R2 by R1 plus R2 into R2 by R1 plus R2, which is 1.8 into, it is 120 by 320. So this is the value. So let us go bottom up now. It is now, so W by L is 45. So what is 1.8 into 120 divided by 320? It is now 0.675 volt. Come here, it is 100 exponential minus 6 into 45 into 2.275 whole square. This is the current. Current is 340.3 microampere. If you substitute here into 2, it is now under root of 2 into 340 exponential minus 6 into 200 exponential minus 6 into 45 plus. So it is now 2.47 millisiemens. This is millisiemens. So this into how much is RD? RD is actually 1.2 K. So this into 1.2 K. Okay, it is now 2.96 volt per volt is the gain, cos magnitude. So with this 2.96 as the gain and this as so and so, and we will get CG input. Okay, this is now, so it is 45 exponential minus 12 into 1 plus 2.96 inverse. It's actually 60.2 picofarad. This is what is C out. What is CG? Cin is equal to 45 exponential minus 12 into 1 plus 2.96 plus 45 exponential minus 12. It's actually 223.2 picofarad. So C in, C out we know. C in is this much, C out is this. We know CC is equal to 0.1 microfarad. R in is nothing but R1 parallel R2, which is 200K in parallel with 120K, which is 200 inverse plus 120 inverse whole inverse is 75K. So let us substitute these values and try to find different frequencies. F1 is 1 over 2 pi R in CC. So it is 1 over 2 pi 75K 0.1 microfarad. So it is 75 exponential 3 into 0.1 exponential minus 6 into 2 into pi. Now that is actually 21.2 hertz. What is F2? F2 is 1 over 2 pi R out C out. R out is actually 1.2K. It is now 2 pi 1.2K. C out is 60.2 picofarad. So it is 2 into pi into 1.2 exponential 3 into 60.2 exponential minus 12. It is 2.2 megahertz. 2.2 megahertz. What is F3? It is 1 over 2 pi R signal into C out. It is 1 over 2 pi R signal is, how much is R signal? I think it is 100 ohm multiplied by C out is sorry, this is not C out, this is actually C in. Sorry for that. R signal into C in, because here these two R signal into C in. So this is what is F3. It's not R signal into C out, it's actually R signal into C in. So Cin is 223 into, okay, picofarad. So it is now 2 into 5 into 100 into 223.2 exponential minus 12. 1 over that is, it is 7.13 megahertz. So if I remember all these things, so let me find out what is dB of this also. What is AB in dB? Exactly 20 log of 2.96. So what is 20 log of 2.96? It's actually 9.42 dB. If I come here, if I come to this, so this magnitude is 9.42 dB. 42 dB. This is 22 hertz. This is 2.2 megahertz. This is 2.2 megahertz, whereas this is 7.1 megahertz. You can see this is 9.42 megahertz. This is 22 megahertz first cutoff frequency. Second cutoff frequency is 2.2 megahertz, and the third cutoff frequency is 7.1 megahertz. So what is the bandwidth now? Bandwidth is 2.2 megahertz. Gain bandwidth product is bandwidth multiplied by gain in volt per volt. Don't substitute in terms of dBs. It's actually 2.2 megahertz into 2.96. 2.96 is the magnitude. If you multiply these two, it is 2.2 into 2.96. It's actually 6.51 megahertz. You have to exactly write something like this. So the frequency should increase, the gain should increase as the frequency increases. The slope should be something like this, and it should be flat. It comes here, you can see it again comes down. Don't randomly write something like this. So I have seen most of you writing the frequency response very casually like this. So this is F1, F2, F3. So this doesn't have any meaning at all. So you can see there is no change in slope at all. When you're writing the frequency response, carefully write something like this. It goes like this, then there is one change in slope, and slope should change again. Can you see? Suppose if it has went like, it would have went like this. So you can see there should be again a change in the slope. So come down by 3 dB. So this is F1, this is F2, F3 can approximately write wherever there is a change. Please, for God's sake, don't casually write the frequency response like this. So don't calculate F1, F2, F3. So this is totally wrong. So make sure that you are writing this as a frequency. This is frequency. This is gain in dBs. Indicate this as 3 dB. The difference is 3 dB. The way how it is written here has to be this type. So you have to write what is F1, F2, F3, and their corresponding values like this. So this is one of them is highest one, this is the least one. Suppose instead of this has 100 ohm, if this becomes 1k, if this becomes 1k, can you see what this happens to? Will it not become divided by 10? So will it not become 0.713 megahertz? Suppose if this R signal is 1k, then this becomes 0.1, then the bandwidth becomes okay, this will be 713 kilohertz. So this will become the bandwidth provided R signal becomes 1 kilo ohm. So then this is the bandwidth, because then this becomes F. Okay, now then the frequency response will totally change. The F3 will become somewhere here, which is 750 megahertz. F2 remains there, so and so. So then, of course, if I write this, the gain, of course, let me just write it this way. So this goes like this, and this is somewhere here 750 megahertz, and then it comes down here, and then this how it goes. So this is now f3, this is now f2. So then what is the bandwidth? Bandwidth will be this will be the bandwidth. So you have to be careful while writing the frequency response. So whichever comes, whose cutoff whose frequency is less, that will become the dominating one, which will decide the bandwidth. Okay, hopefully this is clear to all of you.